Well, thanks everyone for coming. We have a good time today. So I'm pleased to introduce Stephanie Milani. She's a final year PhD candidate in the machine learning department at Carnegie Mellon University. Her research focuses on building reinforcement learning agents to address human-centered and use case-inspired challenges. She was a 2024 Future Leader in Responsible Data Science in AI and Rising Star in Data Science. And her work has received outstanding paper awards at the ICML workshop and a Best Paper Award at the NeurIPS Gen AI for Health workshop. So we're very happy to have you, Stephanie. So please, the floor is yours.
Cool. Thank you for the kind introduction. Hi, everyone. Thanks for coming. So today I'm excited to present my research on rethinking AI agents from the lens of human reinforcement learning. So I was excited to be invited to give this talk at the University of Windsor. And so I asked ChatGPT if it could maybe help me plan my day around this talk. And when I asked ChatGPT about this, this is the response I got. So it's very encouraging, but it's not quite what I was looking for. I already know kind of these high-level details, and this is kind of like technically correct, but I'm looking more for something like this, where instead it's managing my schedule for me. So it's setting my alarm for a particular time. It's letting me know about potential upcoming meetings that haven't been planned and asking questions about tasks it can do to follow up. And I think more broadly, this kind of illustrates a trend in the AI landscape where it's shifting rapidly from these more conversational to these more agentic systems. But what are AI agents? I think let's get on the same page about what that means before we proceed. So in my definition that I'm using is from Russell and Norvig's AI, like seminal AI textbook. And essentially an agent is anything that can be viewed as perceiving the environment through sensors and acting on the environment through actuators. And that's very broad. So that covers not just physical robots, but also agents that can take actions in these sort of more web-based tasks or environments. So that ones that can, for example, operate computers. And already these AI agents are being developed and to play an increasing role in the world around us. So for example, they're being designed to make sequential decisions in areas like education, where they might provide personalized tutoring to thousands of individuals. We're also seeing it being developed for things like game playing companions and robotics and more. And importantly, these agents are being designed to act as decision makers in these human environments. And so as a result, a key question for the future of AI is how to build agents that operate well with people. And so in my work, I've covered 3 challenges that I think are important. They're not the only challenges, but we'll just talk about a few of them today. So first, it is likely infeasible for every single use case that we might have for these agents to have this like massive agentic model to cover all the possible goals that we might want it to achieve. And so as a result, we need a way to understand what these agents should be developed for by capturing these important specifications. And if not, we risk abandonment. So for example, one issue with previous decision support medical AI was that it interrupted the workflow of doctors. So instead of being designed to work well with how the doctors actually saw patients and interacted with patients, it got in the way, and as a result, it was abandoned. But instead, we actually want an AI agents that can work seamlessly with doctors to actually promote more efficient and effective patient care. So that hopefully this can lead to better human outcomes overall. Second, we might want to be able to learn from people in more naturalistic ways. So rather than doing things like manually indicating preferences by pressing buttons, it would instead be nice to provide, let's say, various modalities of feedback to personalize and update models for our use cases. So for example, maybe you're not necessarily a morning person when it comes to meetings or like classes. And so it'd be nice to be able to provide this type of feedback to your AI agent assistant in order to get a schedule that meets your needs. And third, we might want to understand the decision-making process of these agents. So in order to achieve high performance, current approaches often use these very large, uninterpretable networks, even in tasks like games. And for example, in this Tesla example, these drivers were reporting a surge in what's called phantom braking, where the Tesla seemed to stop at moments where it was kind of unclear why it was stopping. And this actually resulted in a lot of folklore. So some people had reasons for this happening that seemed very normal, like there wasn't an issue, like there was a speed limit change coming up. But others thought it could be due to sensor failures, such as thinking that shadows were obstacles. And so this can lead to a lot of unhappiness with the product and also a dissolution of user trust. And transparent decision-making can help foster appropriate trust and safe deployment in these high-stakes scenarios. So this is not a real example of what a car can currently do, but perhaps there can be explanations that these autonomous vehicles can provide to help promote this trust. And also this is useful because it can help developers debug when these agents have issues, right? So if there is an issue of thinking shadows are obstacles, developers can use these interpretable models to actually understand what's going on. And these challenges all share a common theme. So they arise from the need for AI agents to operate effectively in human environments through interaction. And so human-centered reinforcement learning takes human-centered AI and reinforcement learning to explicitly prioritize human factors throughout the design process of these decision-making agents, all with the goal of addressing human-centered and real-world challenges. And so that brings me to my work. So I've worked on developing algorithms for reinforcement learning agents to learn more efficiently. Also, I worked on this challenge of understanding and specifying goals, learning from people, and finally, interpretable decision-making. And I'll just talk about a subset of this work in this talk. Cool. So today, we're going to talk about these three components of my work. So first, we're going to talk about understanding and specifying goals. So how can we actually determine the specifications for AI agents to optimize? Second, we're going to look at learning from people. So when we have these more fuzzy or human tasks, how do we actually get AI agents to learn to perform these tasks? And in particular, I'm going to talk about our work on developing a benchmark for this. And third and finally, we're going to look at how we can actually create human understandable AI agents. So I'm going to motivate this work on understanding what goals we should specify to agents through a very particular use case, because the idea is that we want to develop AI agents that can align with the use cases that we have in mind, right? And so one area that I think that can actually be impacted by AI agents is in the mental health. And this is because it's a crucial public health issue where 1 in 8 people globally are living with mental health conditions, according to the WHO. And unfortunately, when people finally overcome the barriers to seeking help with these challenges, they again faced another barrier, which is that they face often months-long wait lists. And this bottleneck exists because therapists are very overbooked. So in addition to supporting current professionals with AI agent productivity tools, AI agents could also potentially be used to train even more mental health professionals, so decision support or training support in educational contexts. And so to create a system that aligns with our use cases, we can use a human-centered design process to figure out not only if this could be actually a useful tool, but also how we can maybe build this tool to address key challenges in the pipeline. So what we did is I conducted interviews with 5 trainees and 7 experts. And this resulted in around 7 hours of these semi-structured interviews, which essentially just means that you go in with a set of questions that you might want to ask, but you can still follow different interesting pathways as they arise in the interview. So it's not like a very structured, formal interview process. And so the goal for this was to really figure out what the needs were of these individuals in this particular context. So in this interview process, I discovered a few things. First, training did not prepare the mental health experts for the real world challenges of interacting with patients. So all of them said they did not feel prepared coming out of their training process. And in particular, the way that their training works is they might do things like read through textbooks or role play with their peers of these patient interactions, but they still felt that this was insufficient. And so, sorry about that. Essentially what that means is that if we were to develop any AI tool that could potentially maybe help them with these patient simulations, so maybe an AI agent that could act as a patient, it would need to reflect the diversity of these patients, so having different conversational styles. And finally, all of them were actually enthusiastic about the possibility of AI being used as a tool for training, which I actually found to be quite surprising because oftentimes when we talk to people about AI, there's a bit of a fear that it's not going to be used correctly, and there's a lot of skepticism around it. But all of them were very enthusiastic about this potential of it as an educational tool. And so taken together, we realized that we could actually create AI-powered patient simulations with the following goals. First, fidelity to real patients, and second, effectiveness for training these mental health professionals. So what we did is that we constructed this solution. Sorry, I'm not sure why someone keeps ringing my doorbell. Anyway, I'm not expecting anyone. So second, so we built this solution grounded in psychological principles and involving these conversational styles that we identified in the interviews. So in particular, what we did is that we take a pre-trained large language model, and we take this thing called cognitive models from psychology, which I can talk about in more detail later if you're curious. And essentially at a high level, what this means is that you take the patient's symptoms, the situation that brought them into therapy, and their kind of underlying thoughts and belief patterns, and you have it in a very structured manner. And so we use that to program the large language model. And we have a set of conversational styles that the large language model can take on that was developed with our co-authors who are experts in psychology. And then we use that to program the simulated patient. And what they do is they role play a session with a trainee. And at the end of the session, the trainee can then basically do a quiz that's asking them to formulate the cognitive model that was used to program the large language model. So it would be essentially like, what is the situation that caused this individual to come to therapy in the first place? And they would fill that out. And then because we've programmed the large language model with a ground truth cognitive model, we can just display that to the trainee to give them feedback on their answers. So this can help them learn this key kind of competency of cognitive model construction that is present in cognitive behavioral therapy, which is a specific type of therapy. Cool. And I'll just give an example of the conversational styles that we identified. So you don't have to read the blue part just to see the difference. So here, this is the reserved conversational style, and this is the verbose. And I think you can already see a distinction in the responses. Maybe one of them kind of resonates more with you. And so to actually evaluate this tool, we again do this human-centered process of evaluating with real mental health professionals and trainees. So in particular, we evaluated this tool with 20 experts and 13 trainees. I'll just talk about the results with the 20 experts here. And what we did is that we asked them to interact with GPT-4 and our tool, Patient Side. And we asked them to compare along the axes that we identified as being the goals for designing the system. So training effectiveness, whether this could be useful in practice for actually training mental health professionals, and fidelity, how similar it is to real patients. And so overwhelmingly, the experts preferred our tool over GPT-4 along both of these factors. And we also asked them to compare to the traditional training methods, such as peer interactions. And they also found that it was more realistic and effective for training versus this type of method. And finally, we also asked them to assess the presence of the conversational styles, whether they felt that those were actually useful. And all of the experts preferred to practice with these different conversational styles. So they found them to be more reflective of the actual patients, which validates kind of our use of this human-centered design process to have these different specifications in the conversational agent. And so I'm really excited to see even more work in the space of simulating individuals as training tools. So we see this not only in the mental health area, but also more broadly in education. And there's also a lot of really exciting opportunities for future work here. And additionally, I'm excited about even more broad impact of the work. So in addition to being the headline story for CMU SCS News, I also found a non-English tutorial of our work on YouTube, which indicates that kind of more globally, this type of work is, people are excited about this type of work. Cool. So in that, we've seen how this kind of human-centered AI design is one way that we can actually determine the goals for which we want the system to achieve. And then we've seen how we can also use human evaluation to validate that these choices were correct before we actually deploy such a model. And we've shown it in this case study of mental health training, but there's potentially more broad ways that we can actually do this. So maybe I can pause here and see if there are just any clarifying questions.
Any questions from the audience? I think just continue and we'll have questions at the end.
Okay, sounds good. Yeah, and hopefully there'll be no more doorbell ringing. Cool. Great. Okay, so we've seen that. And now I want to talk about our work on learning from people. So how can we actually get agents to perform these kind of fuzzier goals once we've identified them? And this is for a couple of reasons. So you'll have noticed that in the previous work, there is no reinforcement learning, but reinforcement learning is a really powerful tool, in particular in the presence of a well-specified and also able to be verified reward function. So it's achieved very impressive results in environments that have these properties. So for example, we had the Diamond Challenge, which is a challenge in Minecraft where you task an agent to find a diamond. And we want this because in Minecraft, It's great to be able to get diamonds. It enables you to do a variety of things in the game. So you can build better armor, you can build better like weapons and tools, and it's a kind of key thing that players will do in game. And also it's a challenging sequential task. So you have to achieve all of these milestones along the way to getting a diamond. Now, importantly, you can actually write down an easy to verify reward function that specifies the goal of achieving a diamond, right? So you can just say that if the agent gets a diamond, you get +1, 0 otherwise. And this is very sparse, so this is not a great reward function, but it's very easy to define it, right? And also the game state tells you whether this is achieved or not. So if the agent has it in its inventory, you've achieved a diamond. Otherwise, you haven't. So it has these two key properties, which means that there's a clear reward function, and also it's very easy for us to check whether it's true or false. But real-world applications don't necessarily look like that. So many of our goals are fuzzy, not well specified, human dependent, and also they're like a little bit harder to verify. So for example, in the simulated patient case, we want the simulated patient to act like a real patient, but maybe we don't want it to reveal too much information right away. We maybe don't want it to like have too much insight into its own problems. And additionally, for things like, I don't know, cleaning the house, it's also unclear when the agent should actually stop cleaning. Like, what does it look like to actually fully clean the house? And so here, these objectives are not clear. And also, we don't have a game state to be able to immediately check whether it's true. So as a result, we'll see that we really need to learn from people in order to see whether this task has been achieved. So for example, for cleaning the house, you can maybe just ask the human, is the house sufficiently clean? If the human says yes, then maybe you're done. So there's no clear reward function, and we really need to learn from people to be able to see whether we've achieved these tasks. But evaluating algorithms that learn from human feedback is challenging. So most commonly, the pipeline is as follows. We take this pre-existing reinforcement learning benchmark, we remove the reward function, we then train an agent using often synthetic human feedback of your choice, such as comparisons, demonstrations, and so on. And then you evaluate the agent using the ground truth reward function that you've held out, right? And then you can say whether the agent has achieved the goal or not. And this setup can be great because it simplifies this evaluation process, but there are some opportunities for improvement. So first, it requires someone to write down this ground truth reward function to begin with. And we've seen that that can be difficult, but maybe you can try to do it using the human-centered design process. However, the problem is that many tasks of interest are ones that are easy for people to grasp and intuit and perform, but they're difficult for agents to do so. So these are these tasks. And second, these environments often only support a few reasonable goals. So for example, here, the agent essentially only moves forward or it falls. And ideally, we want a large space of goals because our objective here with these agents is to ascertain whether an agent is accomplishing the correct goal, which might have very specific nuances in how the human wants it to be performed. So if there's only like 2 main goals that the agent can do, it doesn't really get at the kind of heart of what we're trying to evaluate. And so as a result, we proposed this challenge, the Mineral Basalt Challenge, in which agents need to learn from people. So this is the first embodied reinforcement learning benchmark that actually doesn't have concrete reward functions. So we defined 4 tasks, like build a waterfall in Minecraft. So you can see here the waterfall, and also build a house. And so in this case, human feedback defines the actual objective that we want the agent to achieve, rather than just serving as a kind of proxy reward signal. And so we held this challenge as a set of competitions at NeurIPS. And we partnered with OpenAI to provide participants of this competition with pre-trained Minecraft foundation models called VPT, and then also some human feedback, so demonstrations to make progress towards achieving these tasks. And so with VPT, we provided participants with VPT models because it can actually achieve a diamond in Minecraft. So it's already very competent. And so we challenged participants of this competition to more so focus on fine-tuning these models to achieve the goal using human feedback. And the takeaway from this is that human players still vastly outperform AI agents on this challenge, even if you use this kind of very powerful foundation model for Minecraft as a baseline. So here, the top two bars are the human performance, and the third bar is the best performing AI agent. And this is arguably the simplest task of the four that we defined. And so you can see that there's still a large gap in terms of how well human players do versus AI agents. And so to promote the development of algorithms that learn from human feedback, we released two large-scale data sets. So first is the demonstrations data set, where we also partnered with OpenAI to collect nearly 14,000 videos of humans completing the basalt tasks, and the evaluation data set. So I showed before the performance metric, and this is computed using this evaluation data set. And the way we do evaluation is through this process of asking for pairwise comparison of humans and or AI agents completing the basalt tasks. So here we just ask them which player actually created a waterfall. They can say the left one, the right one, neither, or both. And so as a result, we get around 3,000 pairwise comparisons of the task performance. And additionally, we ask a few other questions. So this results in the first multi-objective comparison data set for AI agents, to my knowledge. And so what we do is, in addition to asking about task performance, we also recognize that just task completion might be insufficient to actually understanding all of the different specifications that people might have in mind for evaluating such agents. So we also ask them things like, which player seemed the most human-like? And which player chose a better location for actually building the waterfall. And as a result, if we factor out all of the comparisons, this results in almost 28,000 total head-to-head comparisons along all of these factors and tasks. And so to my knowledge, this is the largest data set of its type. If anyone has any references to other data sets like this, I'd be very curious to know about them. And so maybe unsurprisingly, if we look at this in a kind of factored out way, people still outperform these AI agents along all of these factors. So here again, the pink and the brown are the two humans, and then the best performing AI agent on the for task performance is this orange one. And we can see that if we decompose along all the factors, human players still vastly outperform AI agents. So they not only more often create a waterfall, but they also are more human-like and choose better locations for their waterfall, for example. And so I'm really excited also about the broader impact of overall. So in addition to having this diamond competition that I mentioned for 3 years at NeurIPS, we've seen kind of broader impact in industry and also in academia. So we've seen various algorithms and benchmarks being built off of this challenge. And we've also seen it being used in classroom settings, such as at Cornell and USC, and also in the deep reinforcement learning course with Hugging Face. And then additionally, we had basalt as a competition at NeurIPS for 2 years. And we also saw some broader impact of basalt as well. So we saw it being used in the deep learning course at Boston University, and then also there was a broader interest in it from various news outlets, which is really exciting. And so here, in learning from people, we've not only seen how it can be challenging to actually evaluate agents that perform these fuzzy tasks, but also that these preferences have various facets, and also that aligning these AI agents through human feedback remains an open problem in these kind of fuzzy or agentic tasks. And so next I want to talk about work on interpretable decision making. So how can we actually create these human understandable agents? Like, let's say that we've defined these goals we want the agent to achieve. We have a way to optimize for these goals. Now, how do we actually understand the behavior that the agents are doing in order to achieve these goals? And we'll talk about it in the context of AI assistant agents. So let's say you have an AI agent that can actually act as maybe an assistant to manage your calendar. You might want to ask it why it did particular things. So for example, why did you schedule a follow-up with a particular person? And because AI agents make decisions using these very complex input with very large-scale neural networks, often you might get a response that looks something like that. It's very hard to intuit and understand what's going on. And so more concretely, let's say you have an AI agent that's acting as an assistant to a therapist. Ideally, you might want to be able to give it various modalities of input for their input state. And it would then go through a network to produce an action. So for example, scheduling a session tomorrow with this particular patient. But wouldn't it be nice if instead of that, we could get maybe a set of human understandable concepts that describes the input that results in the agent making that decision? And so a way that we can do this is through concept bottleneck models, which essentially just enable AI decision-making based on these human understandable concepts. So what we can do is we can insert a concept layer into the network. So this would be called the policy for reinforcement learning. So we can insert a concept layer into the policy network in order to make the RL policy interpretable. And this is nice because we can ask questions about not only why an agent made a decision, but also counterfactuals about decision making, such as what would you have done in the case where maybe a patient was not anxious? So here it would send a text to check in rather than scheduling a follow-up. Additionally, this is nice because experts can actually intervene on concept mispredictions. So this creates a really nice human-AI interaction pipeline. So for example, let's say that the agent happens to mispredict that the patient mood is improving, which I think is clear to everyone that this is not the case from this, but let's say there's a misprediction. And let's say it ended up in an incorrect action being taken, so scheduling a session in a month. Now, a human expert can actually come in and they can intervene to correct this concept. So they can say, actually, no, the patient mood is declining. And that can then potentially change the action that the agent is taking to be the correct one. So there's this nice human AI interaction pipeline that is enabled by such models. So this is a nice structure that we want to be able to bring to the reinforcement learning setting. However, previous work in this area had a particular challenge. So in particular, if we think about this from a human-centered lens, there's a key challenge that occurs. So in the concept learning part, we're mapping from states to concepts. In the decision-making part, we're mapping from concepts to actions. So for the decision-making part, we can just use reinforcement learning, right? And all we need is to maybe define a reward function, and then the agent can learn on its own to achieve the goal. But to actually get the state to concept mapping, we need to use supervised learning. So what that means is that we query a human for a label about what concepts are present in the current state that the agent is encountering. The human provides the ground truth label, and then we use that to train this portion of the network. And prior work assumes continuous access to a human expert for obtaining the data to train this network with supervised learning. The challenge is reinforcement learning can be quite data hungry, so this resulted in millions to billions of concept labels from a human labeler for even just one task, which is totally infeasible for a human to be able to do. So in this work, we ask the question of whether we can do better to actually reduce the number of labels that are queried from a human to actually produce this human understandable concept policy. And I won't go into details about the algorithm, but we designed this algorithm, Licorice, that takes many challenges that arise in the sequential decision-making setting in order to minimize the number of human labels. So just as an overview, one of the components we have is this active learning component where we essentially query a human only for data points that are actually informative about the concepts that are in the image. So if there's redundancies, we don't want to query for that. So if the state to concept network has already learned this concept well, we don't want to just query for more and more data to reinforce known knowledge. And so we first confirm that to evaluate that Licorice achieves the same performance as state of the art, so the one that required or that assumed unlimited access to human queries. We first confirm that we can achieve the same reward. And we indeed confirm that we can achieve the same reward as state of the art across a few environments. But given that our goal is to actually use fewer human labels, we actually look at, we compare under a more limited budget. So here we're going to look at the number of queries on the y-axis, and then the pink is ours and the brown is prior work, and so lower is better. And we can see that we use significantly fewer labels across all environments in order to achieve the same performance. So here we've achieved this high performance and also tackled this human-centered challenge of limited labels. And doing so required kind of rethinking this training pipeline from the perspective of both reinforcement learning and human-centered AI. And a natural question here is, well, your goal is to reduce the number of human labels. Why not just try to take advantage of these powerful vision language models? And specifically, what we can do is that for the state to concept portion of the network, we also define this prompt for the vision language model that reflects what you would ask a human annotator. So for example, you'll need to label what you see in the image with specific instructions of how you can do the labeling. You can put these into these powerful vision language models, ask them to label the state, and use that for training. So we do that, and we evaluate our algorithm Licorice and with a human or simulated human annotator, and then we evaluate it using GPT-4o as the vision model annotator. And we can see here that vision language models are not there yet in terms of their ability to act as human annotators or in lieu of human annotators, but there's exciting opportunities to improve. For example, using algorithms to promote human AI complementarity. So maybe asking humans for some labels and vision language models for simpler labels, or just directly improving the spatial reasoning ability of these vision language models. And so there's a lot of really exciting future work there. And additionally, as a quick note, if we want to have this decision-making portion of the policy to be of a particular form, let's say a decision tree, because maybe we want to run a verification algorithm or have a human inspect it before deployment, we can use some of our previous work on learning interpretable policies for both the single agent and the multi-agent setting. And then a human can then go in and inspect it before deployment, for example. And so in this work, we've shown how designing algorithms for agents may require rethinking it from the perspective of not only sequential decision-making, but also human-centered challenges like human annotation burden. And we've also done an investigation of whether vision language models can actually help in this instance. And we've shown that they could assist, but not fully alleviate the human annotation burden. And so that's the work I want to talk about today. And I can just quickly go through some of the future work that I think is exciting, and then we can have more of a conversation at the end. So as a broad overview of future work, in my work, I've worked on kind of the intersection of reinforcement learning foundation models and use case human-centered AI. And so moving forward, I'd like to continue working in this space with a few key kind of goals. So I'll go through each one of them now. So first, I'm really excited about the possibility of developing more personalized and naturalistic human-AI agent interactions. So for example, I'd really like it if we could interact with AI agent assistants in a more natural way and specify our preferences in a way that's more natural and also have it be personalized to our goals. And additionally, so far, with interpretability, we've shown how we can build these interpretable agents such that humans can maybe interact with or verify that the decision-making process makes sense. But actually, humans and AI might have different capabilities. So for example, powerful AI agents can actually achieve superhuman performance on some tasks. So I'm thinking things like Go, for example, or even like, let's say, AlphaFold. But the challenge here is that we don't quite understand how these agents can achieve this performance. So if we could have a way to inspect or interrogate the decision process of these agents, we could then potentially leverage that to improve human understanding and decision-making for these tasks. And I envision that this could be useful in more of an educational context as well. And finally, I'm excited about this opportunity to develop more human-centered AI to support real-world use cases and challenges. And so in particular, this could be useful in the simulated patient setting, but also more broadly. So in the simulated patient setting, we saw that the trainee could interact with the simulated patient in just one round of training. But actually, patients interact with therapists over multiple rounds. They have sustained interactions with their therapist. Additionally, therapists have various training competencies that they must master. And also there's maybe evolving preferences and perceptions over time. And furthermore, there are other applications that could actually be useful for this human-centered AI design process. So maybe we have games where we can kind of evaluate what humans want from the non-player characters and design agents to achieve those goals. Or maybe in an educational setting, we can figure out what teachers and students need from these AI in order to design them in a way that reflects their goals. And so that's all. Thank you for listening, and I'd love to take any questions.
All right, thank you. Nice talk. All right, are there any questions from the audience? Yeah, just put up your hand and we'll bring the mic to you. I mean, I have this question to start off. So, so you have these interesting examples of you've trained these AI systems to do mental health, like a psychiatrist, and playing Minecraft, finding the diamonds or making the waterfalls. So how do you train? Like, what is the training step like? Like, what are you giving as input?
Sorry, for which task?
Well, for either of them. So, like for the psychiatrist, for example, like what is the training step like?
Yeah, so that's a great question. So in the mental health case, it's actually really challenging to, as maybe you're pointing out, to write down exactly what kind of type of feedback you might want to give to these agents for training. So actually, what we did is we just had a prompt-based technique is the initial sort of setting. So for that, we specify like the cognitive model, and then we give that as input to the large language model and tell it to act as a simulated patient. And then at the end, we do the human evaluation. So you can envision that perhaps you could use that evaluation data for fine-tuning or further training. But in our case, we just looked at it from a prompt setting. I'm happy to talk about other tasks if you'd like, but that one is challenging, yeah.
What about the Minecraft one is really interesting, right? Because that one must be hard to train. Like you had video, I should show, but how do you give that to a model?
Oh yeah, so that's a good question. So what you can do is you can so it results in a series of state action tuples, right? So the video consists of like an image frame and then an action that was taken. And so you can essentially just decompose it into a sequence of state action tuples with then a preference evaluation from the agent at the end. And then you can use that to give feedback to the agent over the two trajectories. So you can kind of envision, like if you map it to the, let's say, natural language setting, it would be similar to like the standard RLHF setting of like two completions of a prompt, and then you provide feedback. And yeah, so you could design a reward model for this. We didn't do that, but one kind of next step that we think would be really exciting is if someone actually used the data that we released of all of these preference comparisons and then trained a reward model and verified that it works well in this more fuzzy task setting.
Okay, let me open the questions up to the audience again. Okay, we got one here. Spencer, can you pull let's hope the mic works. Okay, good.
In the simulated patient scenario, when you were asking the trainees and the experts to evaluate their experience with GPT versus what was the patient side, were they aware of which model they were talking to while they were evaluating it, or did they only know at the end after they provided their results?
Yeah, that's a great question. So yeah, so that's an important component of experimental design. We did not tell them which one they were evaluating. And so they did not know which of the two, or they didn't have a sense of which one should evaluate better. They were totally unaware.
Any other questions? Oh, we got one over here. Oh, okay, yeah, good. Sorry, I couldn't see.
All right. So, hello. One quick question. It was about the second section when you were discussing the various fuzzy goals, particularly when it came to the competition you had between I believe there were some of the agent models and then the actual human participants, right? In terms of building and making a waterfall, making houses. I think if I remember correctly.
Sorry, did you get that?
No, I did not get the second part.
We're gonna try with the other mic.
Sorry, I'm trying to get. So I'm trying to get this over here. Yeah, can you make come up?
Yeah.
Hello.
Yeah, here, just
Hello. Sorry for the delay. Okay, so this was just a quick question about. This was in the second section. You were showing the results of that little competition thing you had between the various agent models and I think the human participants, right? In terms of making a couple of things in Minecraft and all that. So one of the categories that you said was one of the fuzzy goals that was judged in the end was most human-like in terms of what they built, right? I was wondering, like, how were the models graded on this? Like, what were some of the like the I guess the checklists or whatever? What were the grading criteria there?
Yeah, so this is a really great question. So we asked the human evaluators to evaluate along these different factors, but we didn't provide necessarily a super detailed list of how they should evaluate for things like human likeness. It was more about their own judgment. Actually, in a work that I didn't cover, we actually investigated the specific question of human likeness, so what factors influence people's perceptions of human likeness in a different video game. And we found that human likeness is not kind of like the same for everyone. So people have different beliefs about what human likeness looks like. And also if they know that it's an AI versus a human, they might have these preconceived notions of what AI can and cannot do, which influences their assessment of human likeness. So I think you're right that diving into this even more and having an even more like in-depth investigation of what human likeness means in this context, for example, would be really interesting and exciting future work.
All right, thank you for that.
Yeah, thanks for the great question.
Any final other questions? If not, then let's thank Stephanie one more time.